hoping to have them posted by end of the week, if not end of, or weekend. So, yeah, keep your eyes open for that. Let me know if you have questions, comments, concerns. I think that's the only one. Yeah, only announcement. So, finally getting into talking about drugs in this class, and we're going to start with the depressants. Alcohol is a good place to start, and yeah, let's dive in. So, several of the drugs we'll be talking about, I try and put a little historical perspective. None of the material on the exam comes from these. This is just background stuff. This is, yeah, history and anecdote and whatnot. So don't worry about studying any of these introductory pages for any of the drugs we go over. But alcohol is very interesting because it has human civilization, the development of human civilization is definitely intertwined with this drug, for sure. There are quite a bit of anthropologists that study past that think bread is the foundation of civilization. The making and this, baking and producing the ingredients for bread is what brought people together to make civilization. There's also a very distinct camp within those ranks that think it was actually beer that did all of that. And it makes sense because it looks like the earliest beers were made, like so many discoveries in science and civilization, by accident. And the thought is that early civilizations, definitely Sumerian, Egyptian, when they would grow grain, they would either take the grain and store it in clay vessels, or they would bake it into bread and store it in clay vessels. Those would then be tucked away underground or in caves or somewhere, and then because they're clay, they're easy to break, they would break or crack or somehow allow water to seep in, and then the grains or the bread would get wet and they would ferment with the wild yeast and produce a very rudimentary type of beer. But getting to this class, or coming back to today, this is something that was used and celebrated for a good 6,000 years ago. By these civilizations. Beer was used not only for its social properties, but also as medicine, has religious significance, as you see here. This is a picture of a figurine that was found in a Sumerian dig, or a dig in a Sumerian site, however I should say it. The name of this goddess is Ninkasi. She was the goddess of beer and brewing for the Sumerians. So, very valuable liquid for these civilizations. Wine, similar. It was thought to be similar, when grapes were harvested and allowed to just sit out and ferment, came wine. Wines were used in Mediterranean cultures with a number of different properties, again, outside of the social benefits, but it's clear that early winemaking attempts were very rudimentary and they didn't understand how patient you have to be with that beverage. As if you've ever tried to make wine and you let it ferment for just a couple of months, the alcohol is there, but the taste is ghastly. And so, yeah, from what I've read, a lot of these early accounts, wine was not only adulterated with a lot of spices and things like that because its taste was so poor, it also was diluted down. It's kind of interesting because these cultures did not appreciate drunkenness. So sobriety was valued in these cultures, but they saw the advantage of having alcohol, definitely in social events and that. But it sounds like not only was it adulterated with a lot of spices and things, so it was actually drinkable, but they would dilute it with water, 1 to 6, 1 to 8, wine to water, very common ratios. So it was a very dilute type of drink that was used back then. But anyways, outside of the social lubricant properties, it also could be used for other things in the culture. Big jump in this field came when isolating alcohol or the process for isolating alcohol was discovered. This was done in the Middle East. There's about 1,000 year window when this process was discovered. It's one of those that there's, depending on who you read, there's many different descriptions of who invented it and how it was invented, but some of the earliest ways that it was isolated, this is called an alembic pot, if you're familiar with it. So in the bottom here is where you put your beer or your wash or your mash. So this is the fermented grains or fruits that contain alcohol at a very low, depending on the yeast you use, less than 15% alcohol in here. And you put it on a low flame. And as we all remember from chemistry, alcohol, ethanol, boiling point is lower than water, so you boil it low so that the water stays in its liquid phase. The ethanol goes to a gaseous phase. It can evaporate up this bad boy here, and then when it comes into the neck here, it will condense out because it's cooler up here. So it crashes out into the water phase, and then you trap that down in this vessel here, and you get a much higher percent alcohol. And this was a huge discovery, not only for its social properties, but for its medicinal properties too, as having isolated alcohol was a lot, you could do a lot more with it than just dilute alcohol in some beverage. In the Middle Ages, across Europe, and then later on here in Australia, due to the fact that their understanding of how to not contaminate their own water sources, drinkable water was very scarce in quite a few areas, leading to people really just got by on weak beers and things like that, and no one would even touch water because they were scared of it, but they would live exclusively on that, or they would drink exclusively that, so led to heavy drinking populations in several areas of the world, and thought to give rise to some of the mutations that lead to alcoholism now. And the last little anecdote that I love throwing in, Cambas Society, I believe that's right, in the area that's now Bolivia, has a party, or they have fiestas, they have these several day parties that they drink this 90%-ish alcohol, so roughly 180 proof. And it's interesting because you usually don't, well, one, you don't drink alcohol at this high percent, except for very specific, or yeah, if you really know what you're doing. But all reports about these fiestas is that they're incredibly peaceful, and that's kind of contradictory to a lot of history. Usually with a lot of drunkenness, you get a lot of fighting. Not here so much. These people apparently are at peace enough inside themselves they can drink the hard, the heavies, and not get into it. So, all right, a few little things. So, diving in. Alcohol PD analysis. This is a GABA-A agonist. All right, GABA-A receptor is a chloride channel. So activation of the GABA-A receptor causes an increase in intracellular calcium. Chloride. Chemistry. Chloride, sorry. Increase intracellular chloride. That'll be important in just a minute here. But the other thing about this drug is it has terrible potency. Looking at this, so here's our dose response curve here, percent effect on the Y, concentration drug on the X. Meperidine, talked about before, this is Demerol, kind of a classical opioid now that still is around, but not so much. But shown here as this dose response curve is more in line with the common pharmaceutical that we would take. So 10 to the minus 6 to 7, so these are micromolar type drugs. Micromolar to nanomolar is usually where you want to be with the drug, really in the nanomolar. Micromolar is still pretty poor, but more readily accepted. Ethanol is way up here in the millimolar scale, several orders of magnitude up. So terrible potency. And now, your thought exercise for tonight is to figure this out or think through this, because everybody's going to go home and study tonight, because we just got an exam done, you want to jump on the next stuff. But most alcoholic drinks have about 14 grams of the drug per drink, all right? And as I was saying, most drugs are usually in the mid to microgram quantities per dose. A blood alcohol content of 0.1%, so we all know national average for illegal is 0.08, right? That's beaten into our brains in this country. But 0.1% translates to 100 milligrams of alcohol per 100 mils of blood. All right? How much blood do we have in circulation? 5 liters, very good. So this is roughly 1 mg per mil in blood. So it would be 5 liters would have 5 grams of alcohol in circulation. That's 1 mg per mil, 1 gram per liter. 5 grams of ethanol in circulation in a 5-liter volume, but you drink multiple drinks. Usually it takes 2 or 3 drinks to get to an illegal ethanol content. Why would it be if we have 14 grams per drink, but we only have 5 grams in circulation at that? So ponder that. As far as PK goes, absorption from the stomach and intestine, so this is an orally absorbed drug, with all of the bells and whistles that go along with it. Slow absorption, long latency, essentially saying the same thing. Large first pass effect, so lots of processing in the liver in the first pass effect. So here's our plasma concentration being plotted as a function of time. We ingest our ethanol. Here's our latency period. Very slow onset of this drug into circulation. Okay? Another thing not on the test, just this is in here because, well, we know if you're being evaluated for sobriety, if you get pulled over, they use a breathalyzer. We won't go through all these parts and all of this. This is just the anatomy of a breathalyzer, and then this is a spectra analyzing the different parts of ethanol. But the idea is that this is such a small molecule, and we have it in such high concentrations in our blood, the capillary beds, in the pulmonary capillary beds in our lungs, allow alcohol to diffuse into our lungs, and we actually breathe it out, which is why the breathalyzers work. And it's just kind of an interesting detail about this drug, which is very specific to this one, right? So, yeah, but not on the test. Okay, again, small uncharged molecule. That's what we want, right? This gets across the blood-brain barrier with no problem. Here's the molecular structure of ethanol. I don't expect you to know it for a test. Just 2 carbons, we've got no charge, and it can get across all of these membranes and all of these layers without problem. Yeah, so distribution good, absorption bad. Now, metabolism, 2-step process. First step is done by one of 2 different enzymes. Second step is done by 1 enzyme. Alcohol dehydrogenase, a term that a lot of people know for breaking this down. So it takes ethanol and converts it to acetaldehyde. Same thing with cytochrome P452E1. Remember that. CYP2E1 breaks down ethanol. Know it. Like the back of your hand. As you can see, slightly different processes in terms of what reducing equivalents we're going to use here. You don't need to worry about any of that. Not testing you on your enzymology, we're testing you on the drug. So, ADH, CYP2E1 break down ethanol into acetaldehyde, okay? Again, don't worry about the steps involved, just know that either of those enzymes, mostly ADH, but both of them can come into play and they form acetaldehyde, right? Then the final step here is through aldehyde dehydrogenase that will convert this molecule into acetic acid, and that can either just be peed out or recycled back into, that's a great molecule for all kinds of things. So get recycled back into the building block pool in our cells and whatnot. But this is how it's broken down. Just a quick aside, there's, so the notion that people who are alcohol intolerant, especially those who have an Asian genetic lineage, the misnomer is that they're deficient in ADH, alcohol dehydrogenase. Actually, it's ALDH. Aldehyde dehydrogenase is what people suffer from, and you can see it through their physiology. When these people consume alcohol, they get red and flushed and really hot. That's a buildup of acetaldehyde. That's acetaldehyde toxicity. So it's actually an ALDH deficiency, not an ADH deficiency. Do with that what you will, but that's the case. All right. So we just went over this here. This is just another representation of the breakdown. We've got ADH here, CYP2E1 here. We're breaking down ethanol into acetaldehyde, and then we are breaking down acetaldehyde into acetic acid with aldehyde dehydrogenase. However, here's one drug to know. Disulfiram has been used as a treatment for alcoholism for a long time. It's really fallen out of favor because, well, one, you have to take it to have an effect, and compliance is horrible with this drug, understandably, because it makes you feel horrible. If you take it and you take alcohol, you get sick and flushed and red, and it's crappy and it's not fun. It definitely will steer you away from wanting to drink, but again, you wouldn't want to take the disulfiram knowing what it does to you. So yeah, it is used, but mostly under duress anymore. Anyways, so we'll talk a little bit more in a bit about this, but pharmacokinetic tolerance to this drug would look like this. If we're plotting blood alcohol level as a function of time with two different users, one who's more naive or an occasional user versus a chronic user, you can usually see this pattern where the chronic user's blood alcohol won't reach the same as an occasional user just due to the processing that they do much more efficiently. And again, yeah, talk about that in a bit, but one of the biggest baddies about drinking alcohol is alcoholic liver disease, and it has a progression where chronic long-term alcohol ingestion, and this one usually takes decades to do, what can give rise to a fatty liver. Fatty liver is a hot topic of research right now with a number of different drugs and models being put in place for how this all happens, because we also have non-alcoholic fatty liver disease. But alcohol ingestion over a long time can produce a fatty liver. Long-term result with that would be alcoholic hepatitis, so infection in the liver, and then long-term, well, shorter term there, but this can lead to cirrhosis. A lot of these stages you can regress from if you stop drinking, or at least clean up in certain ways, but once you get to these stages, once you're cirrhotic, you're pretty much done. I hope, yeah, I don't know if I should do trigger warnings in this class, but this is a cirrhotic liver versus healthy liver. I was hoping most people are in science, so a disgusting liver wouldn't be too bad. Obviously, this won't be on the test, but just goes to show what this actually looks like at the cellular level. As you can see, the histology here, an H&E stain of a healthy liver has this great integrity, and you can see how well the liver tissue fits together, and then its vascularization here, not so much on the cirrhotic side. Lots of integrity lost there, just worn away, dead cells, tissue, fibrotic, it's gross. And lacks a lot of functionality, so gross. Quick reminder, alcohol follows zero order kinetics for elimination. A lot of concentration versus time. Looks like this with linear decay, and then zero order, so regardless of the concentration, it has the same processing. At maximum, it's 120 mg per kg per hour. Old stuff, but yeah, this applies to alcohol, so we need to remember it. Now, getting into the nitty-gritty about what ethanol does in our system. We'll look at this poor representation of the neuron. So we've got several different channels and pumps or transporters. Sodium, here's our voltage-gated sodium channel. This is the one that opens up, allows for sodium in, and that in sweep, or the upswing of the action potential. Sodium in and potassium out to rectify that. Chloride in, this is the one we're really going to focus on in a minute. We also have chloride transporter. So I think that question came up before about energetics for transporter. Usually transporter or pump are terms that are used with something that needs a energetic transfer, an ATP, a GTP, usually a tertiary phosphate that needs to kick off to give energy. channels and pores just open up, or channels are pores that just open up and don't require energetics. So that's it. Follow up and something. So, and then we have our sodium, potassium, ATPase here, and this does all kinds of stuff. That's great. What's really important here is the chloride channel, our GABA A receptor. So holding this neuron at negative 60 millivolts in this example, and why this is important, or this, how this works. Again, if we set up a neuron or a cell and we're expressing our GABA A receptor, put a recording cathode in there and record the actual membrane potential. We have a resting potential here of about 60 millivolts. If you put GABA onto this cell, so GABA is hitting its receptor, it causes a decrease in the membrane potential, so dropping it down even further, so making it harder to hit that threshold level to trigger an action potential. GABA with ethanol on board causes it to go even more electronegative, right? It gets even harder to trigger these cells. Here's a picture of a GABA A, well, a model of a GABA A receptor. You can see multiple subunits that make this up. So here's our cell membrane. This channel is sitting in the membrane, outside, inside the cell, as it shows. Chloride will come in, going down its concentration gradient once this opens up, and you can see these areas. Benzodiazepine we'll talk about next time. GABA, the endogenous ligand, bound here on the extracellular face. Barbiturates and alcohol bind here. Some steroids can bind here. Picrotoxin we'll talk about in a bit that inhibits this channel, binds here, but that's, yeah, these are just an example of the things that bind to this channel, causing it to open and allow for influx of chloride, causing the membrane potential to be even more negatively charged. All right, so here's an in vivo experiment. Ethanol discrimination protocol. All right, we did the basics of this already, but let's walk through it again. You have a cage. You have a mouse in a cage. Attached to the cage, you have two different vessels with something in them. One just has sugar water. One has sugar water plus ethanol. All right? There's also levers, and then there's just a recording device here. So in this instance, there's no actual reward other than what's coming out of the bottles, what's being dispensed. So if the mouse pushes this black lever, it gets a drop of sugar water. If it pushes this purple lever, it gets a drop of sugar water plus ethanol. All right? Very simple setup. Trying to control everything except for the one variable of presence of ethanol. Which would a mouse prefer in this situation? And the results are fairly obvious, but plotting the number of bar presses between the two, so you put them in for 30 minutes and observe them, count the number of times it presses each different bar, lever, pedal. It will press the ethanol containing roughly 3 to 1, 4 to 1 times compared to the sugar water, okay? Meaning it prefers this to just sugar water. It prefers the feeling of the ethanol, or prefers something about the ethanol. However, what's important here is that we know that this is a GABA A receptor activity, because if we dose that same mouse with picrotoxin, which is a GABA A receptor antagonist, prior to this, it really nullifies these results. Dose a mouse with picrotoxin, stick it in the cage, it doesn't have a preference. It'll push these indiscriminately as it doesn't feel any difference between the two vessels, okay? Meaning that effective ethanol is driven by activation of the GABA A receptor. Questions on that? How does this sound, everyone? Excellent. Nice. All right. Okay, let's take a step back. Let's take a drink of water. Okay. So much of the effect of ethanol, at least the early effects of ethanol, the enjoyable effects, originate in the amygdala. Okay? So we talked interneurons and projection neurons before. In the amygdala, we have an interneuron, which is a GABAergic neuron, right? it releases GABA as its neurotransmitter. This interneuron in the amygdala will release GABA onto this projection neuron, which has a GABA-A receptor on it, okay? These neurons, these projection neurons, can either be serotonergic, norepinephrine, or glutamatergic, and they go out to different areas of the brain. But we would say that this projection neuron is under the control of this GABAergic interneuron, okay? And again, looking at gross manifestation of all of this, we have these sensory inputs that come in from any aspect of our body, any part of our body. Any of our senses will feed things into our brain. Various areas of the brains will take this information, relay it down into the amygdala. And then the amygdala will have a response we're going to talk about in a minute. But this area is very important, and this is the basic flow of how this information goes and why ethanol affects the situation like it does. A couple of quick asides before we get back to that story. Talking about alcohol and anxiety. All right, since the amygdala is involved in perception of stressful conditions, response to, it controls the response to fear and stress. What happens with a lot of individuals is charted here. When under high levels of anxiety, one very modern, well, classical now, but one, I don't know, socially acceptable, but one well-established way of dealing with anxiety is through drinking. You start drinking, you feel better, you get a relief from anxiety, and that's what happens. However, there are a number of people who are genetically predisposed towards alcoholism, okay? Some of the genetic polymorphisms are listed here. So specific genetic mutation in ADH, specific subset of ADH, dopamine D2 and D4 receptor, as well as GABA-A receptor. Certain mutations in these genetic products lead to a predisposition towards alcoholism. So people in this situation have, once they're, relief from anxiety, but then they get back into an anxious situation that makes them anxious, back to drinking, go through this cycle a bunch of times. And even if you don't have a genetic predisposition, if you choose to do this over and over again, you can develop alcohol dependence. And at that stage, once you stop drinking, especially if you are into benders or multiple days of drinking and then you stop, you can go through ethanol withdrawal, right? And as we talked about before, when developing an addiction, you're not just chasing that good feeling, you're also running away from the bad feeling of not having that involved. So on top of having a genetic disposition, or just if you don't have that, but you've chosen to use alcohol over and over again, the withdrawal can cause anxiety, which will lead to promote drinking, and long-term manifestation of these cycles will lead to alcohol addiction, all right? So what we're going to talk about now is how alcohol will increase GABA activity. It decreases output from downstream neurons and will lead to depressed fear response. And the molecular description of how that works we'll get into right now. So, a couple of players we need to know. Neuropeptide Y, NPY, this is an anti-stress peptide hormone produced in the brain. Corticotropin releasing factor, or CRF, is a pro-stress peptide. Biggest thing to understand from the slide is that CRF binding to its receptor causes an increase in NPY production. I would like you to remember a couple of players here. So going up to the diagram on the right, we've got our CRF binding to its target receptor. This is a GPCR that's coupled to G-alpha-S because we have adenylyl cyclase here. Also can be known as adenylate cyclase, but same enzyme, adenylyl cyclase here, is activated by the G-alpha-S subunit. That will cleave ATP into cyclic AMP. The cyclic AMP will bind to the inhibitor bound to inactive PKA, phosphokinase A, just no PKA. Activated PKA will then translocate into the nucleus where it binds to inactive CREB. CREB stands for cyclic AMP response element binding protein. Don't even bother remember all that nonsense, just remember CREB. pKa binds to CREB, activated CREB finds its CREB binding element in the promoter region of the NPY gene, and transcription is turned on, making a bunch of gene products for NPY, leading to, after transcription translation, leads to an increase of NPY peptide in circulation, all right? That's a whole thing. Remember CRF binds to its receptor, coupled to G-alpha S, activates cyclic AMP, will activate pKa, pKa activates CREB, CREB turns on NPY transcription. If you know it at that level, that's more than enough for exams here. Because the bottom line really is, the big thing you really need to know is that CRF binding to its receptor causes an increase in NPY production. Why is that important? Because, as we just went over, let's put all these together. You have stress, right? Exam 1, Tuesday, 4 o'clock. Bring a pencil. I don't have a pencil. Stress. Amygdala produces CRF. CRF binds to its receptor, causes an increase of cyclic AMP and CREB activation, causing an increase of NPY gene expression. NPY is released. So if we look at the actual production of these two hormones here, so what do we got? We got two different plots. So here's our abscissa here, right? This is our x-axis right now. And if you go, they're plotting two things on top of each other. Yeah, if you're up for giving feedback in this class, I was thinking about, let me get back to that. So, CRS relief is measured on the top plot, the bottom plot is measuring NPY release. The further it gets away from the x-axis here, the more of it there is. CRF is our increased emotionality or anxiety hormone. NPY is correlated with decreased emotionality or anxiety, okay? And so as you can see here in this initial phase, we have this release of CRF even. CRF is released, but as soon as this gets into appreciable levels, we see this NPY take over, right? And if you actually flip these over, you can see how this really relates because production of NPY shuts down CRF production in a very distinct and well choreographed negative feedback loop, all right? Production of CRF causes production of NPY, causes decrease of CRF production, all right? And that's the late phase, right? The late phase is the NPY production and shutdown, consequential shutdown of CRF production, okay? How this relates to everything we're talking about today, as people know, if someone undergoes chronic stress repeatedly over an amount of time, this is known as anxiety. When you're constantly living at a state of fear, anxiety can trigger chronic ethanol production, consumption, and if you consume ethanol routinely, that actually will decrease the amount of NPY produced. So the actual consumption of ethanol over a long period of time and certain concentrations will decrease the ability to produce NPY, okay? So there's a direct link to this natural stress response through ethanol consumption. We take the ethanol because it makes us feel better, right? It does this magical numbing of the brain through CNS depression due to activation of GABA A receptors. But it also interferes with our natural stress response. It'll actually tamp down the production of NPY. Okay? How's that sound, everyone? Please, yes?
So if you were to sell us alcohol, it would benefit you to stress us out.
So, the question is, if I sold you ethanol, it would benefit me to stress you out. Nah, well, if I was, yeah, you could argue that. I wouldn't. I'm not into selling ethanol. I am from a moonshiner family, but That's generations ago, so, yeah, but yes, do we have any less wise ass questions? Yes, please?
Is this why people get anxiety? They're really anxious after they drink.
So that's a good, we're gonna get to that, so, yes, what, you're saying people get more anxious after drinking?
Yeah, like the next morning.
Oh, okay, yes, yeah, we're gonna get to that. A good question, do people get more anxious after they drink? We can get to that, that was great, good lead-in. Yes, please.
So you always hear that like a chronic alcoholic can die of withdrawal compared to other drugs.
Yeah,
And why would it kill you?
wow, this is awesome. Have you talked to other people who've had this class? I mean, these are the best lead-in questions I've had. This is on my fourth or fifth year doing this, but yeah. So let me get back to the script. I'll answer it. Yes, why do people feel miserable afterwards? Why do they have anxiety after drinking? Why is that? We'll get into that, but let's go back to tolerance. Take a step back. Tolerance is a decrease in sensitivity to a drug after repeated administration. We've seen this plot before, right? Here's our dose response curve. We've got a plot here. This would be naive or occasional user, frequent user. So, these are people that have drank for 20, 60 years, some people, and they're gonna right shift their potency curve, right? It's less potent of a drug after a while. So you can see here, it still has the same efficacy. Someone who's been a hardcore drinker for 40 years can still get just as drunk at that 40 years he did on his first day, but it's just gonna take more. Tolerance reduces sensitivity. It occurs as an adaptive response, right? Due to our body's desire for homeostasis. But removal of the drug then, that once we're at that new homeostatic level, removal of the drug disturbs that, and that causes withdrawal symptoms. And I showed this, I guess, yeah. So PK style tolerance would look like this if you're plotting blood alcohol level as a function of time. You dose someone. Chronic user has much less alcohol because they break it down faster, and that is shown through molecular studies that show actual enzyme concentrations in these people. So again, here's our breakdown of ethanol. We've covered this. 2 steps in the first part to produce acetaldehyde. 1 step or 1 enzyme involved in producing acetic acid from that product. But if we monitor liver levels of people looking at ADH, ALDH, and CYP450 2E1, we can see in occasional or naive users, they have a certain level, and then much higher in the chronic users. Means their bodies have adapted to process more ethanol. You won't get it as high in circulation, and that's dose dependent too. If you put down a bottle of scotch and then you go, wait half an hour and take a breathalyzer test, I mean, you're gonna have huge amounts in your blood system. But comparing 1-to-1 type of dosing, a chronic user would have much less ethanol in circulation due to their ability to process it more readily than occasional users, okay? So, to start addressing the first question, acute ethanol tolerance is specific to this drug, and it's fascinating. So again, we're looking at plasma concentration as a function of time. Here's our dose. We take our ethanol, here's our latency period, here's our peak plasma concentration. If you evaluate someone, you pick a level of plasma concentration, we'll call it 1, on the upswing, as the ethanol is being fully absorbed and circulated and all that good stuff. And then you take you go to the same person, you go to the same level of plasma concentration after they've peaked and they're starting to come down, and you assay them for anxiety and their ability to move around and use fine motor skills. What's really interesting is on the upswing, the anxiety is down, but their motor skills are poor too, right? That's when the motor skills are affected the most. However, when you have on the downside, when the ethanol is being processed and you're not putting more into the system, but you're at that same level, same ethanol concentration in circulation, you see the anxiety has returned but the motor skills have 2. So this is acute ethanol tolerance. This is a tolerance that happens within one drug usage period, and it's specific to alcohol. On the way up, you have your anxiety is released, but your motor skills are affected. On the way down, but at the same concentration, your anxiety is back, but so is your ability to use fine motor skills. So, acute ethanol tolerance, and that's part of the answer for why the anxiety comes back after drinking. And we'll get into the rest right now. So, we know all this. Here is normal function of synapse between an amygdala projection neuron and a neuron in the PFC. All right, we're looking at glutamate specifically. This is our activating neurotransmitter, right? GABA is our inhibitor, glutamate's our activator. Here's our presynaptic nerve terminal, and we know all this stuff, right? We got action potential comes down here, opens calcium. Calcium comes in, allows for binding of the synaptic vesicle, release of glutamate out into the synapse. Glutamate binds to NMDA and AMPA receptors, as we all know from the first exam. These are on the membrane of the postsynaptic PFC neuron, and these guys activate effector proteins, blah, 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 but excitation of the system is what happens, okay? This is normal functioning. Put ethanol on board, stops it, right? So here again, here's this glutamate neuron right here. Right here is this downstream neuron in the PFC. Here is where our GABA-A receptor is going to be, all right? So this will control this glutamatergic neuron. Let's say GABA-A is activated. We have a more highly negative membrane potential, meaning we stop the action potentials from happening. So we freeze the glutamate in the synaptic vesicles. These calcium channels don't have open. Nothing comes out here. There's no signal, okay? Now let's do this over a period of time. Chronic ethanol use continues this. But what happens is the body thinks, you know, I used to get this signaling and I'm not anymore. I'm going to try and adjust to that. So what it does is it tries to increase the number of players that usually did this normal flow or this signaling before. It'll make more calcium channels to put in the membrane. It'll create more glutamate synaptic vesicles, and it also makes more NMDA receptor. And this part I find fascinating. The expression level of NMDA receptors increases, but AMPA does not. AMPA stays the same, but you've got more NMDA receptors. But none of that matters because we're still frozen in place because GABA-A is still on and we still have a highly negative membrane potential. So we don't have action potential, we're not spilling anything out, but we've got this system that's just built up. Now, stop it. You pull ethanol from the system and everything just dumps out. Calcium channels turn on, but now there's a whole bunch more of them, so you have this massive dump of calcium. You've got all of this buildup of glutamate, just dumps out into the synapse, all over. Then you also have a bunch of more receptors that are ready to take this. So you have massive excitation, and this gets to the point trying to make before. Ethanol withdrawal syndrome, one of the biggest and most severe effects are delirium tremens, or DTs. If you've ever known anyone that has used ethanol, alcohol daily for lots of years, and then they stop, they shake, and it's ugly. This is a horrible condition. All of these things happen. So to get back to the questions that were asked, what happens if you go out on a lash, even if you're not really used to drinking, if you drink more than you're used to, your body has a minor version of this going on. You don't have all of the expression levels happening, but you do have a shutdown of the glutamate neurons. And then when your body readjusts to that, it'll dump more out and it'll allow for activation. And that's part of why you feel horrible. The other part of why you have a hangover is due to the aldehyde. Dehydration and aldehyde poisoning are the two main baddies of a hangover. A lot of it is the aldehyde, it's just kind of toxic. So that makes you feel terrible, the dehydration makes you feel terrible, but this also comes into play because you really froze your system for the night, and then you get a sleep, things rejuvenate, you wake up, but you're still shaky a bit, and that's why this happens, because you're having a new flux of glutamate that's allowed to now signal. But that's just a hangover. Yes, please.
Is that why like some people like if they wake up and they can't beat the hangover, they'll have like one drink and it'll like help?
That's exactly right. Yes. So having hair of the dog or any other ridiculous phrase that we have, if you have an alcoholic drink the day after you've drank a lot, if you're really hungover, yes, it will help you, and that's it. You're making it worse on yourself, but that's exactly why, because you just started over again. You go back to feeling better because you activate more GABA. Anyways, these are the things that happen with alcohol withdrawal symptom. And yeah, the DTs are why you tremor like that massive flux of glutamatergic signaling, or your glutamate tone increases so much you're just not used to it. And it just causes everything to get nuts. And then all these other horrible things happen too. So, okay, questions on that? We'll do a little bit more Tuesday, I guess. Well, get into benzodiazepines or do the rest of it.